This black ring has been cooked onto the stove so many times that ordinary wiping no longer touches it. Now watch what happens when 3% hydrogen peroxide reaches the surface. Tiny bubbles appear almost immediately. The brown film begins to look wet and loose, and within seconds it seems as if the peroxide is eating through years of grease. But this reaction can be dangerously convincing, because bubbles do not tell us what has actually been removed. They may come from food residue, metal, dirt, or peroxide simply breaking down into water and oxygen. To find out what peroxide really does, we need to let the stove cool completely, divide this deposit into 3 equal sections, and test each one separately. The first section receives only household 3% hydrogen peroxide. The second receives the viral mixture, baking soda moistened with peroxide until it forms a paste. The third receives warm water and a few drops of dishwashing liquid. Each section gets the same contact time, the same cloth, and the same number of wiping passes. That matters, because a cleaning video can make almost any ingredient look miraculous if one side is soaked longer or scrubbed harder. Before anything touches the stove, all burners are turned off and cold. The removable grates and burner caps are lifted away, but the burner heads, igniters, openings, and electrical controls are not flooded. Stove finishes differ enormously. A product tolerated by stainless steel may discolor aluminum, attack a painted marking, or leave a cloudy patch on ceramic glass. The appliance manual decides what is safe, not the fact that a mixture came from a kitchen cabinet. A hidden test spot is the first experiment. On the peroxide-only section, the liquid spreads unevenly. That is our first clue. Hydrogen peroxide is mostly water, while grease repels water. The droplets sit on top of the darkest areas instead of soaking through them. Bubbles collect along scratches, crumbs, and exposed metal edges. Hydrogen peroxide is an oxidizer, so it can change some colored organic residues and reduce certain odors. It may lighten a brown food mark enough to make the surface look cleaner. But it is not a powerful household degreaser. It does not automatically surround oily material and carry it into rinse water the way a surfactant can. Now consider the foam. Hydrogen peroxide naturally decomposes into water and oxygen. Light, heat, contamination, and contact with certain metals can accelerate that breakdown. So a violently fizzing patch may simply be consuming the peroxide before it penetrates very far. More bubbles can mean faster decomposition, not greater cleaning power. And if an old bottle produces almost no bubbles, that does not prove the stove is already clean. The peroxide may have lost strength during storage. The second section looks far more dramatic. Baking soda holds the peroxide against the stain, prevents it from running away, and turns the treatment into a gritty paste. As the sponge moves, the white paste becomes yellow, then brown. It appears that peroxide is pulling grease out of the stove. But 3 different actions are happening at once. The paste provides contact time. Baking soda adds mild alkalinity and fine abrasion. The sponge supplies friction. Peroxide may oxidize some colored residue, but the thick brown streak on the cloth cannot be credited to peroxide alone. To prove it, a small control patch is treated with baking soda and plain water at the same consistency. It also removes a surprising amount. This is the part most viral demonstrations omit. When 2 ingredients are mixed and the cleaner scrubs for 30 seconds, the result does not reveal which ingredient mattered. The paste may be useful on a compatible surface, but calling every improvement a peroxide reaction confuses chemistry with elbow grease. There is another catch. Fine particles that help scour durable metal may create micro scratches or haze on delicate finishes. Printed burner symbols and glossy coatings can also wear away. On a ceramic glass cooktop, manufacturers commonly recommend a cleaner and scraper specifically designed for that surface. A razor held incorrectly, a harsh pad, or a homemade abrasive can turn one grease spot into permanent damage. On stainless steel, rubbing across the grain can leave visible marks. On enamel, chipped or worn areas require even more caution. The safest method changes with the stove. The third section seems least exciting. Warm, soapy water makes no volcano and no satisfying white foam around the black ring, yet dishwashing liquid contains surfactants. Each surfactant molecule has a part attracted to water and another attracted to oily material. With time and movement, those molecules help loosen grease and keep small oily particles suspended in the water instead of spreading them back across the stove. Warmth can soften the deposit, but the surface should never be dangerously hot, and cleaner should never be applied to an active burner. After the same 5-minute dwell and the same wiping pressure, the fresh and moderately baked grease transfers readily to the cloth. The oldest carbonized ridge still resists because detergent cannot instantly undo a heavily polymerized layer. A second controlled soak helps. On an approved surface, a manufacturer-recommended non-abrasive pad or cooktop scraper can then lift the softened residue. This is less theatrical than peroxide, but it targets the greasy part of the mess more directly. Now the 3 dry sections can be compared under side lighting. The peroxide-only area is lighter in color but still slightly tacky. The peroxide and baking soda area is cleaner, although faint scuffing may be visible if too much pressure was used. The detergent area has removed the oily film most evenly, and the remaining dark specks are hard deposits that need surface-appropriate mechanical removal. The winner is not one universal recipe. It is the method matched to the material and the kind of soil. Peroxide can still have a limited role. On a finish whose manufacturer allows it, a small amount may help with certain colored organic stains after grease has already been removed. It should be applied to a cloth or contained spot rather than poured across seams, burners, igniters, or controls. It needs a short observed contact period followed by wiping and any rinse recommended for that surface. Gloves and eye protection reduce avoidable exposure, and ventilation is sensible whenever cleaning products are used. What should never happen is improvisational mixing. Peroxide should not be combined with bleach, ammonia, vinegar, an oven cleaner, or an unknown product left on the stove. Mixing cleaners can create irritating or dangerous reactions, and residues from the previous product count as mixing too. If another cleaner was used, the surface should be rinsed as directed and allowed to clear before anything else is considered. More chemistry does not mean more cleaning. So what did hydrogen peroxide actually do to the baked-on stove grease? It wet the surface, oxidized and lightened some organic discoloration, produced convincing oxygen bubbles, and helped carry away material that was already loose. What it did not do was magically dissolve every hardened oil layer. In the famous paste, baking soda, dwell time, and scrubbing supplied much of the visible result. Against actual grease, dish soap performed the less glamorous but more relevant job of helping oil mix with rinse water. The dramatic fizz was the beginning of the experiment, not the answer. A clean-looking patch can be bleached, scratched, still greasy, or genuinely clean, and those outcomes are not interchangeable. Once the stove is dry and viewed under honest light, the lesson becomes simple. Peroxide may change what the stain looks like, but the safest, effective cleaner is the one designed for the soil, approved for the surface, and used with enough time to work.